Welcome back all of you. In the last class, I introduced you about the spin system nomenclature. I discussed what is a strongly coupled spin system and what is a weakly coupled spin system and how are they represented by using Roman alphabets. I said if they are weakly coupled spins, we represent, let us say, two spin half nuclei which are coupled between themselves. We represent them if they are weakly coupled by two letters which are far away in the alphabet. If they are strongly coupled, we use the letters which are next to each other or close to each other, like AB, ABC, like that. And if there are equivalent, chemically equivalent spins, when they are coupled among themselves, I said we can use prime notation. If we have magnetically equivalent spins, we can use subscripts like A2X2, A2M2, A2M2X2, like that, or A for AA prime, XX prime if they are chemically equivalent. So, these things I just briefly touched upon, and I showed you if I have a two weakly coupled spin system, there are four possible energy states corresponding to four energy states like alpha alpha, alpha beta, beta alpha and beta beta. And I showed there are four possible transition using the selection rule for single quantum transition, which is change in the magnetic quantum number between any two energy levels is either +1 or -1. And I showed diagrammatically for weakly coupled AX spin system there are four possible transitions. Fine, theoretically we can, pictorially we understand everything, but you also wanted to understand quantum mechanically how to generate these energy levels, how to understand how the spectrum comes when the spin systems are coupled, whether it is weakly coupled or strongly coupled. I also said for quantum mechanical treatment, two spins we can do fairly comfortably. If you go to three spins, okay, with some difficulty, but beyond that it is going to be a very, very difficult task. So, I wanted to show you, I started how we can use quantum mechanical treatment to get the energy level diagram and also transition frequencies for two coupled spin systems. I took an example of AX spin which are weakly coupled, and I said first of all for the quantum mechanical treatment what you have to do. The first step is to define the set of basis functions to describe the spin system, and I said the basic functions for the first approximation are the true wave functions, especially when you are dealing with the nuclear spin systems. The product of basis function is the exact wave functions of individual spins. That is what I said. So, what are the wave functions? I explained to you. For a spin off nuclei there are two possible wave functions, alpha and beta, corresponding to orientations. Of course, what happens if you have two spins, we will work out and we will tell you. The first step is to find out the wave function, define the wave function. Second step, we have to define the Hamiltonian, and we are dealing with the solution state NMR, not solid state NMR, because there the interactions will be much more and more interactions will come into picture, and we are not going to touch upon it at the moment. So, we will deal with analysis of the spectrum of two weakly coupled spin system in the solution state. So, we have to define the Hamiltonian for such a system, that is the next step, and each nuclear spin interacts with the external magnetic field. This is what we call a Zeeman interaction. In addition to that, between the two spins which are interacting, there is a scalar coupling which is mediated through covalent bond. This is what we discussed about the scalar coupling. These are the interaction of the two nuclear spins mediated through covalent bond through electrons. There is a polarization transfer between one spin to other spin through covalent bond. So, these two interactions have to be included in the Hamiltonian. This is the second step to define the Hamiltonian. Next, third step, we have to determine the energy level diagrams, energy levels of the system, and describe true wave functions in terms of linear combination of basis functions. What does it mean? I said nuclear spin basis functions for spin off nuclei, as I already told you, are alpha and beta are the basis functions. Now, for two spin system, the correct wave functions are simply the product functions of individual spins. What are the product functions? You can think of all possibilities of combinations of these two wave functions for both the spins. If one is in alpha state, other is in beta state. Now, for the one spin, other spin is also alpha beta, then you can take out the combination of alpha alpha, alpha beta, beta alpha and beta beta, all 4 possible combinations you can think of. These product functions are now the correct wave functions for the nuclear spin systems. Okay. And if I have n interacting spins, there will be 2 to the power of n product functions. Remember, there are 2 to the power of n product functions. When we have 2 spins, 2 square, there are 4 product functions. If you go to 2 cube, it will be 8, reasonably big. Go to 4 spin and above, it will become huge. That is the reason I said the quantum mechanical treatment, if you want to analyze beyond 2 or 3 interacting spins, is fairly difficult. So, we are sticking to that. For spin half nuclei, this Hamiltonian is given as h equal to minus gamma b naught into I. This is the general Hamiltonian. We know that b naught is the magnetic field, I is the spin of the nuclei, and gamma is gyromagnetic ratio and h cross is the Planck's constant. Now, what will happen to this Hamiltonian? This gets modified first of all due to chemical shielding. I told you when we discussed chemical shields, due to electronic environment surrounding the nucleus, there is a shielding effect. So, the nuclear spins do not see the correct external magnetic field. This gets modified at the site of the nucleus because of the shielding of electrons surrounding it. So, as a consequence, we have to include that as the Hamiltonian first. That Hamiltonian is B naught into 1 minus sigma into I z I, that is what is written. B naught, of course, the same thing is modified here, expressed in terms of units of hertz, in terms of Larmor frequency, easy for us to work with this system in a simpler way. That is why it was taken in the frequency units, so that we can express in Larmor frequency. And sigma I is the screening constant, that is also we discussed earlier. So, in a situation like this, when you express in Larmor frequency, we already worked out what is the basis, what is the resonating frequency. The resonating frequency is given as nu into gamma into b naught over 2 pi. Here I have put I because now I have to consider 2 nuclear spins. Each of them may have a different chemical environment. So, the resonating frequency corresponding to each of them will be different. And now gamma I, in fact, it should have been nu I, gamma I should be same because with the both I am considering homonuclear case, it is proton. So, that is why instead of gamma I can put nu I is equal to gamma into b naught over 2 pi. I is the resonating frequency, it varies for both the nuclei which I am considering because of the chemical environment. So, the Zeeman Hamiltonian I can write like this. Okay. Zeeman Hamiltonian is h naught into sigma summation of 1 I 1 to n nu I into I z I. N is the number of interacting spins, in our case it is 2. Presently we are considering 2 interacting spins. Okay. So, the Hamiltonian due to scalar interaction we will consider now. Again we have this interaction coupling constant Jij and Ii dot Ij are the interaction between 2 nuclear spins. Now, this being a vector, I said we can expand it in 3 components Ixi, Iy, so Ixi, Ixj, Iy, Iyj and Izi, Izj. We can write it clearly. Now, for n is equal to 4, how many terms you can think of? Let us think of 4 nuclear spins are interacting. For n is equal to 4, we have 4H0 because each nuclei will have a different Zeeman interaction terms. Now, interaction among themselves there could be many. For example, one nuclei, if I consider 4 nuclei 1, 2, 3 and 4, one can interact with 4, one can interact with 3 and 4. Similarly, 2 can interact with 3, 2 can interact with 4, 3 also can interact with 4. So, essentially we have 6 H1 Hamiltonian terms. So, if I consider 4 interacting spins, I have 4 H0 terms and 6 H1 terms. Right now, we are dealing with 2 spins, we have 2 H0 terms and only 1 H1 term. So, now you may ask me a question, we are applying the radio frequency that also interacts with the nuclear spin, it will perturb the system. In addition to Zeeman interaction we discussed as an external interaction, RF also has an interaction, but at the moment we will not consider that because we are dealing with the steady state of the spin system. So, since we are dealing with the steady state, we do not have to worry and we consider only H0 and H1 without interaction of the RF. This is the total Hamiltonian for the 2 coupled spin system. So, once you have this, once you build the Hamiltonian, what is your next step? We have to solve the time independent Schrodinger equation, which is given as h psi equal to E psi. Psi is a wave function, we know that. So, now you know the Hamiltonian and we have to calculate the energy levels, that is easy, we have to now work it out. Okay. And most convenient way of solving this, I told you last time itself, we have to express this in the form of a matrix. This equation can be expressed in terms of a matrix in an appropriate basis set. Okay. Now, for n spins, especially when I am considering 2 interacting spins, we have 2 to the power of n, that is 4 product functions for 2 spins. They are alpha alpha, alpha beta, beta alpha and beta beta. These are the 4 product functions. Okay. So, now we can construct the matrix, diagonalize it to get the eigenvalues and get the eigen functions which are linear combination of the basis product functions. These things we can do. So, we have to write the equation for this. We have to now solve this equation. And what are these? These are the matrix element which we have to now work it out. That is what we are going to calculate to get the energy level, and delta M1 is a Kronecker delta. You know that in quantum mechanics basics, when m is equal to n, this is equal to 1, when m is not equal to n, this is equal to 0. Okay. Okay, this is not 1, m is not equal to n. If you remember, there was a typographical error there. When m is not equal to n, this is equal to 0. So, the matrix can be written in expanded form like this, that is H11 that I have considered. This is 1 1 is the element. If you take one row and one column like this, and you can write down, there is now 4 by 4, we have 4 by 4 matrix, we have 16 elements. We have to calculate all the 16 elements if they are available. If it is possible, if they are existing, we should calculate that. So, for n nuclear spin system, size of the determinant becomes 2 to the power of n into 2 to the power of n. We have got 4 by 4 in the present case. So, 16 matrix elements we have to calculate. Okay. That is fine. Now, we said 2 interacting spins. Now, there are 2 possibilities we can think of. It could be j could be 0 and j could be non-zero. There are 2 possibilities. We will consider that now. Consider a situation when j is equal to 0. Since it is a AX spin system, chemical shifts are different, then nu1 is not equal to nu2, that is one situation. So, we need to consider only H0, because H1 we can ignore, there is no coupling, coupling is 0. When j is equal to 0, nu1 is equal to not nu2, j is not equal to 0 and nu1 is not equal to nu2, then we have to consider both H0 and H1. There are 2 possibilities. Now, we will work out the energy level diagram for both the situations. First, we consider j is equal to 0 and then see what are the energy level diagram. Now, when I consider the 2 equally coupled spin systems, as I told you, I will deal with only H0. I will not consider H1 at all. I am not going to take H1 as the Hamiltonian, especially for working out energy levels. So, the basic Hamiltonian turns out to be H0, which is only these 2 terms, because nu A into Iza plus nu x into Izx. Of course, depending upon how we are going to represent, we have a minus nu Zi for the resonating condition. I did not put a minus n while explaining, but sometimes in some books you can see it is written as nu is equal to resonating frequency minus gamma to b naught over 2 pi, depending upon how it is going to be represented. So, I have taken this as minus, this you do not have to worry finally. Now, the product functions are known, alpha 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 beta, beta alpha and beta beta. So, now I construct the Hamiltonian. So, now for alpha alpha on either side, this is going to be diagonal element, alpha beta and alpha beta, this is going to be diagonal element. Similarly, beta beta, beta beta here is going to be this diagonal. So, there are 4 diagonal elements and remaining alternate elements. Remember, matrix is symmetric. So, if I know H12, I know H21, because the interactions in NMR are mutual. If 1 is interacting with 2, 2 is also interacting with 1. So, in this case the matrix is symmetric. So, we have to consider only 4 diagonal elements and 6, not 6, 5 remaining, we are left with 6 alternate elements I have to calculate. Let us do that. So, wave functions alpha and beta are one important thing you should know, they are orthonormalized. What do you mean by orthonormalized? When you say orthonormalized, alpha operating on alpha or beta operating on beta is always equal to 1. They are orthonormal basis set. If I take alpha operating on beta or beta operating on alpha, this is equal to 0. That is why these wave function, 2 wave functions alpha and beta, I say are orthonormalized. This you would have understood in your matrix and vector analysis, everything you would know those things. Now let us find out the action of spin operators on NMR wave functions. This is important thing which you must remember, because we can work out. We can even each and every term here, when I z operating on alpha, why it becomes half alpha, very basic quantum mechanics, we can work it out. Let us not go into that, because it is enormous time consuming if I have to work out everything. Simply remember these things. If I z operates on alpha, you are going to get half alpha. Similarly, I x operating on alpha gives us the half beta. I y operating on alpha gives half I beta. Same thing, if I z operates on beta, you get minus half beta. I x operating on beta gives half alpha. I y operating on beta gives minus half I beta, half I alpha. These are the things which I keep on using it very often. Now similarly, we can represent like this. If alpha I z operating on alpha, then it turns out to be 1. The reason is I can take I z outside. If I take I z out, then I z operating on alpha is going to be half alpha, half alpha. So half I can take it out, it is going to be half alpha alpha. Of alpha operating in alpha, as I told you, they are orthonormal basis, orthonormalized set, it is going to be 1. Similarly, if I take beta, for example, beta this one. So I can say this is I z operating on beta is equal to half. So I am going to take half outside beta, and then beta I write like this, which is going to be 1. So it is going to be half. This value is half. Like that, now for each of the diagonal elements, now I took only for the single wave function. What happens if I take the product? It could be alpha alpha in which I z operating on alpha alpha, or alpha alpha operating on, let us say, H0 or H1 etc. operating on alpha alpha. What will happen? Like that, all 16 elements I have to consider out. The 16 elements I told you in the matrix, alpha alpha I consider, and I operating on this alpha alpha, and I calculate the diagonal element. Similarly, all off diagonal elements and diagonal elements I can calculate. So very easy. Now we start calculating the matrix elements. So what the first thing is, first we calculate the matrix element H110. H110, now I write in the explicit form alpha A, alpha x. I wrote alpha alpha as alpha A and alpha x, because now I am able to distinguish two spins A and x here for calculation purpose. Now nu A and IZA is the Zeeman interaction term for A, nu x IZX is the Zeeman interaction term for x spin, and I am considering the diagonal elements. So alpha A alpha x operating on this H0 term with alpha A and alpha x here. So now we can work it out. If you see simple term, what I should do is, there was a negative sign here, I expand it completely individually both the terms. Now if I take individually both the terms, I can say write alpha A alpha x nu A IZA and this one, minus I will say alpha A alpha x nu x IZX and alpha A alpha x. I did not do anything, simply I separated out two items. The two terms were there, I just separated out these interactions. Now we will apply, we just now found out what are the operating rules. When I z operating on alpha, what happens, all those things, action of the different terms, we have found out what are those things. When I z operating on alpha, I z operating on beta, everything, simply remember that, and we use those terms to evaluate this. Now again, this further, since you know I am nu A is operating and dealing with only alpha A. So alpha x I can take it out, because I am not dealing with x spin here. So I can write like this, nu A alpha A operating on nu A IZA with alpha A, and then alpha x this is taken out here, it will become alpha x into alpha x. Similarly, this term I write as minus of, now this x is operating, so I can take out alpha A alpha A. So alpha A operating on alpha A, and alpha x becomes nu x IZX into alpha x. I resolve the terms depending upon which spin is operating on which nuclei. So in this case, I mean which wave function is operating on which nuclei. So now in this case alpha is operating on A, so I took A here, and x was not operating, I just separated out. In this case x wave function is operating on x, I took it like this. Okay. Now I can simply write like this, because you know alpha x I told you orthonormalized set, it is 1. So this is going to be 1, and again beta A, here also alpha A, alpha x, this also is going to be 1, this is 1. So, both are 1. So, this term boils down to this thing, simple term. Now, minus of alpha A, nu A I Z A, alpha A, minus alpha x, nu x I Z x, alpha x. So, it became a very simple 2 terms we got. Okay. Now, further it is the, we have not completed, we will go further. This can be further resolved. What I am going to do is, I will take nu A outside, that is not going to disturb the system, only we are worried about I Z A operating on alpha A. So, I will take out nu A. So, alpha A I Z A operating on alpha A. Similarly, minus I will take out nu x here, nu x when I take it out, alpha x operating on I Z x and alpha x here. So, the terms can be further simplified. Now, you know what did I explain earlier, that is why I said we should remember when I Z operating on alpha is going to give half alpha. So, I take this half alpha, then alpha A is there, you go back here, see carefully, here alpha A is there, this will become half alpha A. So, you can write it as alpha A into half alpha A, half I will take it out, this is alpha A, alpha A. Then what will happen? Alpha A is orthonormal set, this will become 1. So, now you are going to get half into nu A and this will become 1. Similarly, here I will take out nu x, then alpha x orthonormalized wave functions. Now, what will happen? This will become 1. So, it will become half. In the previous example here, if you see here I Z operating on alpha x, this will be again half. So, what we are going to get is H11 only 2 terms, this will become 1, this will become 1 here alpha A, alpha x. The term finally boils down to only 2 things. H11 will turn out to be, I took the minus as a common factor outside, minus of half of nu A plus nu x. This is the first matrix element we worked out. Now, remember you have to work out 16 such elements. Well, fortunately, we do not need to worry, many of them will be 0 and then in this case, and then only we need to work out only 4 diagonal elements. Most of all the off diagonal elements in this case are 0. So, now work out H22. H22 in this case, remember it is alpha beta operating on alpha beta here again. Now, nu A I Z A again I separate out 2 terms, alpha A beta x, again diagonal term alpha A beta x, alpha A beta x, nu x I Z x, alpha A beta x. Now, I again separate out these 2 terms. What will happen? I will since I am dealing with only spin A here, I am going to write alpha A, nu A I Z A alpha A and beta x operating on beta x, this you know is 1. Similarly, I do the similar operation here, alpha A I will take it out, this is becoming 1, then I will take beta x operating on nu x I Z x in beta x. So, thus this will become 1, then again this is a simplified form, I write this equation here and this equation here, and now we have only 2 terms like what we did for H11, same thing you can do. Now, what you can do? Take out nu A outside. Now, I Z operating on alpha gives rise to half alpha. So, half I took it out. So, it will become alpha A. Similarly, I Z operating on beta becomes half beta. So, minus half beta. So, I will take out, this will become minus half nu x, this will be 1. So, what is going to happen? This is going to be minus H22, this is minus into minus plus. So, I can write it like minus of nu A plus half of nu x, or in other words you can write it as half of nu x minus, take out half, it is going to be nu x minus nu A. So, you can work out similarly H3, H330 and H440, all are diagonal elements, all the 4 elements you can work out. Now, the question is what about the off diagonal elements? Luckily, all the off diagonal elements are 0 here. I will show you by working out only one of them. Remaining I do not need to work out. If you want, you can work it out yourself, make a simple exercise. You will see that alpha and here I will take alpha beta, they are off diagonal elements. I am now working out for H120, H1 is alpha here, I mean 1 is alpha, 2 is alpha beta. So, now I am going to write down again I have already expanded the term nu a izA nu x izx resolve into different components here, alpha a nu a izA alpha, alpha beta, and again alpha a I take it out and nu x izx beta x. But you know that this is remaining same, but here what is happening, alpha operating and beta I told you they are orthonormal set, so it is 0. Similarly here alpha, okay, so this is 0 and this is going to be 1 here, this is going to be 1. So, this is going to be like this, and iz alpha operating on this becomes half minus of half beta here, iz beta operating iz beta will become minus half of beta. So, you are going to write it like that, alpha x is there, now beta again coming here, alpha x beta x again they are 0. So, h1 this will be 0, this term is shown to be 0 multiplied by 0. Now, if you expand this term in detail, you take iz beta which is equal to minus of half beta, half into nu x, this can be very nicely written, half into nu x into alpha x beta x, because this half is coming here I have taken it out, but nevertheless for positive or negative does not matter because anyway this term is 0, alpha operating on beta here is becoming 0. So, h12 is 0, off diagonal element one of the term I showed to be 0. You work out for remaining terms, no problem, you will find all the 6 off diagonal terms are 0 here. So, what do you get? You are going to get only 4 diagonal elements with for this matrix. This is the matrix with secular determinant now, which is here, this is what we started with, and we say H11 E1, now all other terms are 0. So, we have only secular determinant like this. So, there are, since all the off diagonal terms are 0, you have only 4 equations and 4 energy levels, very easily from this matrix you can work out. So, okay, now E1 is equal to, this of course simple matrix algebra, I do not have to tell you, H11 E1 is equal to, now you can write it as, this is the first term, diagonal term, then E1 becomes equal to H1, it will become, you go back here, if you do not get confused here, H11 minus E1, so E1 is equal to H110. So, H110 which is nothing but we already worked out minus half nu a plus nu x. Now, E2 we already worked out, that is H2 to 0, you get half into minus nu a plus nu x. Similarly, E3 is H diagonal element this one, and this is minus half nu a plus nu x, and E4 is half of nu a plus nu x. So, we got all the 4 diagonal elements, with that we get all the eigenvalues. Once you get the eigenvalues, what next? Now, we can find out the frequency of the transitions. We use the selection rule, this we knew that the transition rules, if you look at it, I mean it is changing the quantum number, magnetic quantum number should be either plus 1 or minus 1. Using that I can tell you E1 minus E2 and E3 minus E4 correspond to X transitions. From the energy level diagram which I wrote in the last class, you can see that correspond to X transition. Similarly, E1 minus E3 and E2 minus E4 correspond to A transitions. We will work out what is E1 and minus E2. That essentially you have 2 A spin transitions and 2 X spin transitions. If you go back and calculate here, and you will see that find out the E1 minus E2 difference, E3 minus E4, E1 minus E3 and E2 minus E4, you calculate simple equation, linear equations are there, and you will find out 4 frequencies, 2 of them overlap. For example, in this case I tell you 2 A spin transitions are at identical frequency. Similarly, 2 X spin transitions are at identical frequency. That means there are 4 transitions, but 2 of each transition for each spin are overlapped. As a consequence, for A spin we get a single frequency, a single peak, for X spin we get a single frequency. But it appears single, but 2 are overlapped, you should remember that. When you make the quantum mechanical calculations, you know that. Now, as I assume one condition, chemical state of X is larger than delta A. This is just an assumption, it can be anything. You can make this as delta A or this as delta X, it is your nomenclature, does not matter. So, in this just to show the spectrum, I have assumed that delta X is larger than delta A, and this is the type of spectrum. In the 2 AX spin system which they are coupled, weakly coupled, A and X are, and J coupling is 0. When J coupling is 0, chemical states are far away separated, they are weakly coupled, and you get only 2 transitions, one for X and 1 for x, well separated singlets. That is what you are going to get, and you can see, you have seen by quantum mechanical analysis for 2 coupled spin system, when j is equal to 0, you are going to get 2 peaks of identical frequency, identical intensities well separated, and each of them have 2 frequencies overlapped. Okay. This is E1 by E2 and this is E2, E4 and E1, E3. So, this correspond to X transitions, this correspond to A transition. Now, we will consider a situation, 2 weakly coupled spins A and X. In a situation where nu1 is not equal to nu2, of course, that has to be because of Ax, and in that situation now j is not equal to 0. We will bring in j interaction now. What do you have to do when you bring in j interaction? You have to bring in H11 also, H1 Hamiltonian also. In the previous case we ignored H1, we took only H0. Now we have to consider both H0 and H1, and then same procedure. Of course, now we already know the wave functions, only we have to construct the matrix and get the eigenvalues and solve the secular equation, get the eigenvalues and eigenvalues and then get the frequency of transition. That is what now we have to do in this situation. Now, since time is up, what I am going to do is I will stop it here. In the next class we can analyze this 2 weakly coupled 2 spin system with j not equal to 0. So, in this class what we try to do is quantum mechanically we try to understand, taking 2 weakly coupled spin system, we first constructed the wave function, then we defined what is the Hamiltonian, we constructed the Hamiltonian also. Then what afterwards what we did, we have to calculate the eigenvalues for that. So, we express in the form of a matrix which is a secular equation. We already know that h of m, Hmn minus delta mn, we have wrote that equation, that secular equation when it is equal to 0, we express in terms of the matrix. We have 2 spins, we have 2 to the power of n into 2 to the power of n, there are 16 matrix elements for a 2 coupled spin system. But when you assume the j coupling is not there, all the off diagonal elements are 0, we calculated and showed that only 4 diagonal elements are present, and using these diagonal elements we calculate the transition frequencies, they are nothing but the eigenvalues, give the transition frequencies, and there are, using the selection rule, there are 4 transitions allowed, 2 for A and 2 for X. 2 A transitions are identical frequencies, 2 X transitions are also at identical frequency. So, that means instead of 4 peaks you get only 2 peaks, in each of them 2 transitions are overlapped. If I assume one of the chemical shift is quite large compared to that, maybe X or A, when I assume that X is quite large and it is coming at the down field, A is at the high field, I showed in a simple stick plot only 2 peaks you can get for 2 weakly coupled spin system with j equal to 0. So, next class we will analyze the situation quantum mechanically when j not equal to 0. Thank you.